Hello, and welcome once again to the Posh Physics 262 studios, where we are now about to, I'm doing it again. We're now about to do, I believe this is chapter 27. When I said doing it again, what I meant was I'm terrible with chapter numbers. So I believe chapter 27 is our introduction to magnetic fields, and we've already gone over a lot of this in class, but I wanted to make sure you guys had something to take a look at once again if necessary. So, introduction to magnetic fields. As I mentioned in class, I think it's important to recognize that the root of the magnetic field discussion and the magnetic force discussion comes from exactly that, a discussion of the, doesn't only happen in our classroom, happens at home too. I'm sorry, not home. It happens in the Posh Physics 262 studios too. All right, I'll get my old stinky one from 26 years ago and see if this is still working. All right. So the root of this is what we call, I called it F sub L. I told you I was going to tell you what F sub L stands for. F sub L stands for Lorentz. And there are two physics guys named Lorentz. One is Lorenz and one is Lorentz. So this is the Lorentz with an Lorentz, if that matters to you. If you go on in physics, you'll see that there's two of them. And they both worked in similar fields. So there's a little bit of a strange overlap there. In any case, the Lorentz force is Q V cross B. And I mentioned by analogy with the Coulomb force, I mentioned that in the same way that we took Coulomb's law, F equals or is proportional to Q1 Q2 over R1 2 squared R1 2 hat or R2 1 hat, I can't remember. In any case, in the same way that we built an entire structure based on that equation, we're doing the same thing with this equation here. And it's not quite as evident because it's a little bit funkier, but here we go. So, just a reminder, a couple things. First thing, this is what we know. We know that there are these things that are called magnets. And we know, we knew this for thousands of years. We'll scratch the north and the south. We knew this for thousands of years. What we didn't recognize with that was that this was actually a magnetic field. And it wasn't until after we had decided there was such a thing as electric fields that made our life easier that we said, oh, maybe there's a thing called a magnetic field that makes our life easier, i.e., that allows us to describe observable behavior that would otherwise be difficult to describe. And so we, in fact, discovered that, and we define this thing called a magnetic field. And you guys will recall, just by convention, we say the magnetic field goes from north to south, so out of a north pole into a south pole. You will also remember that as opposed to electric charges, where you can have a thing that's called a monopole, i.e. you can have a single isolated positive or negative charge. With magnetic fields, you can't. With magnetic fields, you can only have a dipole. And you guys will remember, actually, I'm going to go ahead and draw this in for just for comparison purposes. You'll remember that if we have one charge, but once we have a dipole like this, you guys will recall that the field lines are something like this. And so this structure here, this dipole structure of the field, is essentially the dipole structure of the field here. And so that's how we get this analogy that this is a magnetic dipole. And the point here is there is no such thing as a magnetic monopole. If you cut a magnet in half, you just end up with a smaller north-south magnet that now just does this. Okay, so those are let's see, that's one conceptual thing. The other conceptual thing is actually contained within this force here, and I did mention this in class, but I'm going to go over it again, just because this is another instance where it becomes very clear that what we are doing as physicists as physicists, is describing the external world. As I mentioned also, there are some very complex, high-level things to explain why is it there is this thing, this thing called a magnetic field. But really for hundreds of years, at least 100 plus, we had this magnetic field. We described how it worked, but we had no clue why. And even now, the ultimate source of it, that's an open question. Depends upon if you believe in some specific theories or not. Then, okay, well, I won't get any further into that because it's well beyond my level of expertise. All right, so what's the point here? Oh, the point is that this is a really strange force, and this is why I say it becomes really clear that we're describing the world without necessarily understanding it. Because what we're saying is, if I have this pen and I'm pushing it, I expect it to move away. And we know equal and opposite reaction. I'll feel the force on my fingers. Oops. I'll feel the force on my fingers, and this thing will eject and or will react to the force that I put on it. However, this force, just look at it. It's got this cross product in here, and we know cross means it's perpendicular to both V and B. I mean, how strange is that? That's saying if I have this here and I push it this way, it is going to move this way. I mean, can you understand why that is? I mean, we can describe how it is, but can you understand why it is? I can't. But I understand how it is. This described how it happens. Okay, but it is, of course, even weirder than that, because what this law right here, or description right here, says is if this pen is just sitting here and I push it, nothing's going to happen to it. But if it's moving and I push it, so let's see, what do I have to do? If it's moving this way and I push it this way, it's going to go this way. It's like, whoa, Nelly. Oh, excuse me. In that case, it would be going this way. All right. So it's moving this way. I push it this way, and it moves this way. Really strange. Okay. I think I'm actually going to cut this off right here for this. Oh, no, I'm going to do one more thing while we're talking about just very general introductory things. Once again, we already talked about this in class, but what we know is if we do have a magnetic field, and you'll notice I didn't put the source in here because it doesn't matter what the source is. If there's a magnetic field here, then another magnet will want to line up with that. So if it's going from north to south, it will want to do that same thing. Here's the south, and it's going to continue on that line where north is going out. Okay, so South Pole attracted to North Pole attracted to South Pole. So it wants to line up, and if it can, it will actually, get right in contact, right? So we'll have a bunch of magnets that are lined up north-south, north-south. That's what they would like to do. Okay, I think that's enough of a conceptual introduction, and everything else is just kind of implications of all this. So I am going to stop here, and then we'll move on with a little bit on specific forces. If my computer wants to wake up. It's the end of the semester. My computer's saying, I'm done. I hope it lasts another few weeks.